The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@yvcc.edu and I'll respond as soon as I can. Alrighty, so today we're going to wrap up section 11.5, but before we do that, do you have any questions from yesterday's homework? Anything you'd like me to look at before we go on?
Email.
Yes, Richard.
Can you do a logarithmic equation and then turn it into an exponential and then reverse it just so I can see it one more time?
So you want to go from a logarithmic equation to an exponential and from an exponential to a logarithmic equation?
Yes, please.
Okay, you betcha. So let's say we've got log base x of y equals z. So the base is x. So writing this in exponential form, it'd be x to the z power equals y. So the base stays the same, but the players change places, so to speak. If we have an equation a to the b power equals c, writing that in logarithmic form, that would be log base a of c equals b. Once again, the base stays the same, but the players change places. Anything else? More examples?
Can you do one with an exponent in it, like a fraction exponent?
Oh, okay. So let's see. 4 to the 1/2 power equals 2. So log base 4 of 2 equals 1/2. Is that what you wanted?
Yeah, thank you. I mean, I'm doing them right. I just wanted to see you do it again.
Okay. And a question that somebody asked yesterday, let's see, what was it like? Log base 7 of 3 equals n plus 2, something like that. So then that would be 7 to the n plus 2 power equals 3. And this whole thing would be the exponent because this whole thing has to be grouped together. Okay.
Yeah.
Let's see. Or, oh, I know what it was. It was this. It was, let's see, 2 to the 8th power n equals n plus 5, let's say. So that would be log base 2 of n plus 5 equals 8. But you need to have parentheses here to group that all as the thing you're taking the log of. That was the problem. It was something like that. So you got to be careful how you keep things grouped or make sure they get grouped. All right, anything else? Well, today's focus is going to be on this formula. A equals P times E to the RT power. And we use this when we have something that's growing or decaying continuously. All right, let's take a look at our first example. Let's see here. I'll write this a little bit better. It says continuous compound interest. That's the title. Already it says continuous. Now, if it was compound interest that wasn't continuous, we use that other formula. A equals P times the quantity 1 plus R over K to the KT power. That whole thing. Okay. An initial investment of $2,000. So that's P. Earns 8% interest. So that's R, which is converted into a non-percent or a decimal number, compounded continuously. What will the investment be worth in 15 years? So T is 15 years. So let's read it again. It says continuous compound interest, an initial investment of $2,000 earns 8% interest compounded continuously. what will the investment be worth in 15 years? So A equals P, which is 2,000, times E raised to the R times T power. That's supposed to be a multiplication there, okay? So again, I can predetermine 0.08 times 15 if I want, or I can just leave it in parentheses. So I'm going to put in, let's see, 2,000. And then e to the x. So I've got 2,000 e, and that's what's showing up in my calculator. 0.08 times 15. 0.08 times 15, close it up, equals, and I get 6,640.233845. And it says, it doesn't really say anything, but in terms of rounding, this is money. So we would automatically round to the nearest cent, since we can't spend a fraction of a cent. So this 3 would round downwards, and we'd have $6,640.23 as our final answer. Any questions about that particular problem? All right, let's take a look at another example. This says determining the previous balance. An account now contains $3,610 and has been accumulating interest at 8% annual interest, compounded continuously. How much was in the account 4 years ago? All right, since it's being compounded continuously, we're going to use that formula again. It says an account now contains $3,610. So we're going to go backwards. We know the final amount. The interest rate has been 8%, so 0.08. It's been compounded continuously. How much was in the account 4 years ago? So T is 4 years. But we want to know the initial amount. So we're working backwards. We have the final amount. It says that basically in the title, determining the previous balance. So A, 3610 equals P. We don't know what P is. E to the 0.08 times 4. Okay. I need to solve for P. So in this case, what I'm going to do, I'm going to predetermine 0.08 times 4, which is 0.32, okay? To solve for P, I'm going to divide both sides of the equation by e to the 0.32 power. So now I get P equals $3,610 divided by e to the 0.32 power. So on my calculator, 3610 divided by e to the 0.32 power, and I get 2621.398024. Again, this is money, so I'll round to the nearest cent. The 8 would round up, so $2,621.40 would be the final answer. So notice we ended with less than we started with because we were going backwards. We end up with this much. How much did we start with? Any questions on that? All right, next problem. It says, bed bugs, if not checked, the population of a colony of bed bugs will grow exponentially at a rate of 65% per week. If the colony currently has 50 bed bugs, how many will there be in 6 weeks? All right, so it's growing exponentially. It's a population, so we're going to use A equals PE to the RT. If not checked, the population of a colony of bed bugs will grow exponentially at a rate of 65% per week. So R is 65%, which is 0.65, and that's per week. Now, previous problems were per year, but this is per week. If a colony currently has 50 bed bugs, so the starting amount is 50, how many will there be in 6 weeks? So notice the rate is per week and time is in weeks. So A equals 50 times E raised to the 0.65 times 6 weeks power. All right. Again, I could predetermine 0.65 times 6, but I'm just going to go ahead and leave it. So I've got 50 times e to the 0.65 times 6, close it up, power. I get 2470.12. Now, let's see, how many will there be in 6 weeks? Rounding to the nearest bed bug, which would be right there, the amount would be approximately 2,470. Any questions about that? I hope you sleep well tonight thinking about bed bugs. Okay. Here comes another problem. It says, the Big Easy. I don't know, that's just the title. New Orleans has steadily won back some of the population it lost in the wake of Hurricane Katrina in 2005. If the current 8.2% annual increase in population remains constant, how long will it take for its population to double? All right, so we're talking about growth rate and increase in population. So we're going to use A equals PE to the RT. It says the current growth rate is 8.2% annually. So that would be 0.082. How long will it take? So T is the unknown. It says for the population to double. So they don't tell us the initial population. All they tell us is that the beginning population is going to double. Well, let's say we just call the beginning population P, okay? If P were to double, how much would you have? Anybody?
P squared.
No, we're not going to square it. We're going to double it.
2p.
2p, there you go. Yeah, because p squared wouldn't quite be the same thing. So the final amount is equal to 2p. You okay with that, Sarah?
Yeah.
All right. So we know the growth rate. We know we're trying to find the time. We don't know the initial population, but the ending population is twice the initial population, okay? So I still don't know what P is, but as we're gonna see, I don't need to know. So watch. Using this formula, we're gonna say 2P equals PE to the 0.082 T power, okay? Now, I'm trying to solve for T. T is wrapped up in that exponent on the base of E, so I can't separate that out at this point. But what I could do is I could divide both sides by p. Now, I want to make sure I don't divide by 0, but I'm fairly confident that p isn't 0, because if we're talking about a population that's 0, why are we even talking about it? Okay, so there's got to be some population. But now I've eliminated p from the equation, even though I didn't even know what it was. Okay, now I'm trying to solve for t. T is an exponent or part of the exponent. So I'm going to take this exponential equation and rewrite it as a logarithmic equation. So I'm going to get log base e of 2 equals 0.082 times t. Is everybody okay how I did that? But isn't log base e natural log?
Oh, yeah.
Oh yeah, there you go. So the natural log of 2 is 0.082 times t. Let's divide both sides by 0.082. And we get t equals the natural log of 2 divided by 0.082. Let's put that in our calculator. Let's see here.
I have a question.
Yes.
How did you get the log E on the other side? I lost connection on that.
How did I get this? Is that what you're asking? How did I get that? Sarah? Hello?
The third one down where it says log.
Sorry, I can't hear you.
Yes.
So how did I get this, right?
Yes.
Okay, so if I take
Yeah. Yes.
if I take that equation, 2 equals e to some power, e is the base. So changing that to a logarithmic equation, I get log base e of 2 equals that. So I'm changing it from one form to the other.
Okay, I see it. Thank you.
And then
Oh,
log
I
base,
didn't even notice that happened. Okay.
we
yeah,
played
yeah.
a whole inning of baseball and you were off
And
in
I
the
missed
field
it.
somewhere. Okay. And
Okay, now I
log
got it.
base e is natural log. Okay. Now let's put that in our calculator. So natural log of 2, make sure you don't push the log button, but natural log of 2 divided by 0.08. Oops, 0.082. My bad. I forgot to put the 2 there. And I get 8.453014397, blah, blah, blah. And let's see here. They rounded it to the nearest 10th. So the 5 would round up. So we're going to get t is approximately 8.5 years. Okay. 8.5 years. You all right with that?
Yeah.
Now, again, notice the initial population. We didn't even know what it was. But it didn't matter what it was, because if we put the initial population here and double that over there, and then divide out the original p, we end up with 2 equals all of that, right? So let me ask you this. Let's say I put in some specific number for p. Let's say I put in 3,000, okay? And I did this exact same problem with the same growth rate, but the initial population was 3,000 and the ending population was 2 times 3,000. Would I get the same answer? Yes, I would, because instead of dividing both sides by p, we just divide both sides by 3,000 and we'd still end up with this. What I want you to look at is this right here. Before we went to the calculator, the time was the natural log of 2 divided by 0.082. Where did this number come from, the 0.082? What was that?
The rate changed to a decimal?
Yeah, the growth rate, okay? So t equals the natural log of 2 over r. That's a formula. It's sort of a shortcut to what we did here. Anytime you're looking at a continuously growing population and you want to know it's going to double, okay? If you know the growth rate, you can take the natural log of 2 divided by r and get the time. In fact, that's one of the formulas that's in the textbook. It's on page 956. I don't know about the ebook online. I assume that, well, I don't know if the page numbers match or not, but it's right before the exercises in 11.5. It's a formula for doubling time. What if we were going to triple the population? What if everything was the same, we didn't know the beginning amount, but we were going to end up with 3 times that?
You'd replace the 2 with 3.
No, you wouldn't replace the t with 3. What would you replace with 3?
The 2.
The 2. So then you'd end
The
up
2.
with the natural log of 3 over r equals t. Can you see that? Because this would be a 3, this would be a 3, this would be a 3. Anyway, but for doubling time, it's the natural log of 2 divided by the growth rate. All right. Now, let's see here. Let's take a look at another example of doubling. It says double money. How long will it take $1,000 to double if it's invested at an annual rate of 5% compounded continuously? Okay. So how long will it take $1,000 to double if it's invested at an annual rate of 5%? Notice I didn't even put the $1,000 in there, okay? Because again, if we go back and do it the long way, A equals P e to the RT, we get 2 times $1,000 equals $1,000 times e to the 0.05 t. We divide both sides by $1,000. We get 2 equals e to the 0.05 t. We change that to log base e of 2 equals 0.05 t, but log base e is natural log of 2. And then we divide by 0.05. So that's doing it the long way, but we end up with that. So again, that's a shortcut for doubling. All right with that? Let's find the answer. Natural log of 2 divided by 0.05 is 13.86. And I think they go to the nearest tenth, so it's 13.9 years. That's all I've got for you today to wrap up section 11.5. Okay. So I'll be back at 1:15 if you have any questions. Make sure you notice the difference between this formula and that formula.
Can
Here,
you tell me what the difference? Okay, good.
I'm going to.
Okay, good.
Here, this is like we've got money in an account and it's growing, but not continuously. The interest is compounded k times. If it's annually, k is 1, semi-annually, k is 2, quarterly, k is 4, monthly, k is 12, daily, k is 365. But if it says it's compounded continuously, or if we're dealing with a population which grows or decays continuously, that's when we use that second formula, okay? So if it's talking about continuous compounding, we use this formula. If it's talking about monthly or yearly or semi-annual or something, that's when we use that formula. Okay?
Yeah, I got it.
All righty. I'll be back at 1:15 should you have need of me. Otherwise, I'll see you tomorrow.